Yes, welcome in our lecture shunt compensation or FACT devices. Uh, in the last lecture, we have discussed something summary of shunt compensation. Now we will continue with the same topic with some new points. So before going to new topic, just we will take the review. Our objective of FACT devices is to modify the electrical characteristic of existing transmission line because uh, at the second side we are increasing the generation, but the evacuation facility or to transfer the electrical power from generating station to the load center, the main link is the transmission line. And to erect the new transmission line, the cost as well as land and many things are required. So it is better to modify the uh, electrical characteristic of existing transmission line to obtain some points. So what is that objective? The objective number one is to increase the power handling capacity, which we have seen. This is the uncompensated line. The maximum power that can be transmitted is equal to V square upon X sine delta. This is the P delta curve. And with the help of midpoint shunt compensation, the capacity of the power handling capacity of the transmission line get increased with the double. That is the ideal compensation which is connected to the midpoints. Second is to prevent the end voltage or say voltage collapse. This is used for the, we can say that this is used for say radial line. The we are using the shunt compensation to the near to the load, and that is called as a load compensation. So here the voltage profile is not constant, whereas by the shunt compensation we can obtain the flat voltage profile. Third point is the power oscillation. Whenever there is a sudden disturbance, the angle get oscillate, and this oscillation may increase or it will oscillate for a longer time. So with the help of shunt compensation, this oscillation can be mitigated, which will avoid the power swing into the transmission line. And fourth very important point is the improvement in transient stability. So we have seen it in detail. This is the red curve is the without compensated line, and the transient stability is going to evaluate by the equal area criteria. The area of acceleration is equal to the area of deceleration. Then the system will be stable. If your area acceleration area is greater than the deceleration area, the system become unstable. So this is the marginal area for uncompensated line. So we can say that this is a less stable, less chances to stable, and whereas with the compensated line, there is a large marginal area is available, and the system, the power transient stability of the system can be improved very well. So this is the some points which is related to the last lecture. Now, further today's lecture, we discuss the method of method of controllable war generation. It is found that the static war compensator or shunt compensator is very beneficial for the transmission line. But the second point comes into the picture is that how to control the war. So there are two methods. One is the variable impedance type static war generation, where the impedance of the inductor and capacitor is going to vary with the help of some thyristor control, thyristor switch, and their combination of thyristor control and thyristor switch. And therefore, the classification become thyristor control reactor, thyristor switch reactor, TSR, and thyristor switched capacitor. And as the thyristor is a switch capacitor, it is going to vary in step. So uh, there is a one more method that is called as a fixed capacitor thyristor control reactor. So combination of fixed capacitor and thyristor control reactor. So this is the thyristor control reactor. Whereas in the second side, the second method is the switching converter type war generation. So here, instead of using the inductor and capacitor, switching converters are used to generate and absorb the reactive power. And the basic operation of switching converter type VAR generation or VAR absorber is similar to the synchronous motor. So either the synchronous motor is overexcited and underexcited, it active fact devices, but it is a rotating machine. And as it is a rotating machine, it consumes the active power as well as maintenance is needed on the rotating part. So this rotating part is going to replace by the static one. So it is called as a static synchronous generator, SSG, or static synchronous compensator or condenser. So it is a very popular one, it's a Statcom. So this one. So in short, we will see what is the way by which we can vary the VAR generation. So it is quite simple that when there is a inductor, okay, so is a capacitor. So it is a VAR generation because it provides the reactive power to the transmission line. Whereas if it is a inductor, it is a VAR absorber. Or it is absorb the VAR which is from the transmission line. So first we will see the thyristor controlled reactor. So as it means this is the transmission line. We will go in fast because we are taking only the review or summary of this. This is the inductor, which we want to vary the impedance of this inductor to obtain the variable VAR absorber or absorption. So this is the thyristor which is connected in anti-parallel. So this thyristor may carry up to the 4 to 9 kV voltage and 3 to 6 kilo ampere. So as per the requirement, the number of thyristors are connected in series to obtain the system voltage, or number of thyristors are connected into the parallel to obtain the current capacity, and the combined is called as a thyristor wall. That thyristor wall, the important is that when we are giving when the gate pulse is provided, it should be simultaneous. Otherwise, in one string, if one of the thyristor remain off and rest of the thyristor start conducting, that thyristor, turn off thyristor, definitely damage. So this is the care we have to taken. Now we want to control the current into the inductor, and definitely as it is a thyristor control, we are going to control the current with the help of delay angle or delay firing angle, say alpha. So what would be the waveform in short? Say this is the system voltage. In positive half cycle and negative half cycle and so on. So this is the voltage, and now the current is the fire the thyristor is fire in here in such a way that this is the current IL alpha when alpha is equal to 0, means there is a no delay. So this is same for the negative half cycle. So this is same for the negative half cycle. Means here the firing angle is equal to 0. Therefore, it start at the peak of the voltage, and one can see here, this is the lagging by 90 degree. This is the current is lagging by 90 degree as because of the inductor. Now, we will provide some delay angle. So say this is some delay angle is there, system voltage. Will provide some delay angle for 1 or 2 half cycle. So it become clear how the current is going to vary with the help of, say, this is the Now there is a delay angle, and because of this delay angle, the magnitude of current get decreases. Here again the delay angle has been increased, so the current also decreases, and so on. So this is two part. This part is the, say this is the voltage, system voltage, and this is the current I with respect to the angle alpha. So see, this is the delay angle. This is the delay angle alpha 1. Now this is the delay angle which is increased alpha 2, and here the delay angle again increases alpha 3. Whereas this part is the conduction angle. This part is the conduction angle. So if the delay angle or the firing angle is delayed, definitely the conduction angle becomes smaller, and we found the current in the inductor get changes. So this is the way by which we can vary the current into the inductor, and hence this we can obtain the variable impedance, and it is a static variable VAR generation, static controllable VAR generation. So this is the points over this one. So one way vary, this is how the current is going to vary into the inductor. Now what would be the VI characteristic, or say working area of thyristor control reactor? So as this is the thyristor controlled reactor, this is the current IL lagging. This is, say, voltage is there. Okay. So it is a voltage of inductor VL. So say this is the maximum voltage, depend upon the system voltage and the capacity of inductor, those are connected. And this is the maximum value of current can handle by inductor. This is the admittance line of inductor BL, and this is the region, or this is the area in between the VAR generation, reactive VAR generation or absorption can be obtained. So this is the working region or working operating area. So operating VI area of thyristor control reactor. Now the value of current, this value of current is depend upon the angle, delay angle. So this can be understood with the help of one more diagram. Say this is the delay angle alpha. Definitely it is 0 and it is 90, maximum is 90, and the current is, say, 100%. So when the delay angle is 0, here angle alpha is equal to 0, there is no delay, the current will be maximum as per the capacity of inductor, and as the angle increases, delay angle increases, the current also increases, and it becomes 0 at delta is equal to 90 degree. Say here it is delta is equal to 90. So we are not going to conduct, so it become a thyristor. Thyristor is off. So alpha, when alpha is equal to 0, it is on condition, and when alpha is equal to 90 degree, then it is a off condition. So depend upon this on and off, the second part become thyristor control thyristor. So it will give the second example, that is the thyristor switch thyristor switch inductor, thyristor switch reactor. So it is a thyristor switch. So it means that either it is going to conduct or it will be off. So because of these two operations, so current in the thyristor become its maximum value, otherwise it will be 0. So the VI operating area for the thyristor, the diagram will remain as it is. The diagram will remain, same thing is there, same thyristor walls, number of thyristor wall as per the capacity and as per the, say, voltage of the transmission line. So this inductor, this is the voltage, and this is the current IL. This is the current IL, but it is not the function of delay angle. So what would be the VI characteristic? The VI characteristic, this is the maximum value of inductor current. This is the maximum value of voltage. And this is the admittance of inductor BL. So it is not shown by the some area represented here. So it is a thyristor switch reactor. Okay. So it is a simply thyristor switch reactor, because either it is going to conduct the current or it will be off. So this is the second case. Now, third one. Third one is the thyristor switch capacitor, which we have seen. Now, the thyristor switch capacitor, the diagram, this is the voltage. Now, the capacitor, whose values we want to control with the help of static switch, walls, and one small inductor is connected to avoid the heavy inrush current, and at the same time it avoids the resonance. So I C, or capacitive current, this is the V, and same thing is there. Okay, but it is found that once the capacitor is conducting and turn off, the capacitor get charged, and that capacitor charge, and if you are again switching on the capacitor, it will give the switching surge, or say transient, switching transient. So there may be two possibility, is that when the charge capacitor, say for example, this is the voltage across capacitor, and it is switched off over this one. So it will be, this is the voltage V, and this is the charge capacitor. So this charge capacitor voltage VC may be equal to or smaller than the supply voltage. And second case, say first case, when it is equal to and smaller than the system voltage. So this is the system voltage V, and this is the capacitor voltage VC. Similarly, this is the capacitor voltage, and this will be the capacitor charge voltage. So this is the first condition, and this is the second condition. When VC is greater than equal to V, so what would be the correct position to switch on the capacitor? So for first condition, this is the right position to switch the capacitor. So under such condition, it will give the transient free switching, and here it will be the right position to give the say switching free operation. So it means that when the capacitor voltage is 0 or it is partially charged, definitely it will give the transient. So this is the system voltage. This is the system voltage. We'll take the two examples to understand the switching surge, switching transient, or the capacitor. So if the capacitor voltage, charge voltage is smaller, somewhere here, so it will give, say, somewhat, this is the voltage V, and this is the capacitor voltage is equal to 0. So when we switch on the capacitor, it will give the large amount of, say, transient over this one. And when the capacitor voltage VC is somewhat 50%, the transient is smaller. The transient is smaller. So the conclusion is that the capacitor either should be switched on to the maximum positive or positive half cycle, or next positive half cycle. So there is no in between term where the capacitor switch can be switched. Therefore, it is not a capacitor controlled, it is not a thyristor control capacitor, but it is a thyristor switched capacitor. So either the capacitor is going to switch to the positive peak or the negative peak or to the next positive peak. So therefore, it will gives only the thyristor switch capacitor. Now, what is the VI area of thyristor switched capacitor? So definitely it is as it is a capacitor. So here this is IC. Just to remember, this is the VC. In this side, we are taking the current IL, so it is absorbed. And here, generate. The capacitor going to generate the reactive power. So this is the maximum voltage and maximum current, depend upon the capacity of the capacitor, and this is BC. So now again, it is going to switch on, either it is 0 or its maximum value. So the area is not a controllable, so it will work as a switching mode. So this is the for the thyristor control capacitor. Now the next one is the fixed capacitor thyristor controlled reactor. So in this case, the diagram is in this way. The first part is the fixed capacitor. This is the system voltage or the transmission. Now this is the fixed capacitor. It is shunted by inductor and thyristors. So under such condition, this is the fixed capacitor. This is the inductor. The current in the inductor is going to vary with respect to the change in delay angle. So this part is a fixed capacitor and this part is a thyristor controlled reactor. So this thyristor controlled reactor independent work, which is explained earlier, and it is the fixed value. So the combination of this one, the combination of variable inductor and or the controllable inductor and fixed capacitor, the effective value of war generation, can be done. See here, this is the drawback for the thyristor switch capacitor. The variable reactive power generation cannot be obtained, whereas absorption can be obtained in the variable form. So by combining these two, one may obtain the variable generation as well as the variable absorption. So what would be the VI characteristic or VI area, operating area under such condition? So this is the IL and this is IC. The voltage is V. Let we assume that the inductor is more as compared to the capacitor. So here the inductor is higher value. So this is the maximum value of current IL maximum. So in this side, absorb the reactive power absorbed by the thyristor control reactor, whereas it generates. And the capacitor is, the value is capacitor. Deliberately we have keeping some smaller value. So this is, here is the IC maximum. Now In this case, the controllable region for the inductor is this one. And as it is connected in parallel, the effective value of generation can be controlled. So this is also the controllable. So see, the previous drawback is overcome by connecting a thyristor controlled reactor. Now one may use the different value of capacitor. So it become, if you are using a different value of capacitor, it become thyristor switch capacitor thyristor control reactor. Means it is a combination of these two. It is the combination of these two, and it can be obtained for, this is the, say, BL, and this is BC. Okay. So this is the way by which we can obtain the static war generation. Static war generation means it is a static war generation as well as the absorption, both with the help of thyristor controlled reactor and thyristor switch reactor, thyristor switch capacitor. Now the next is, which is very important, is the Statcom. So Statcom. So what is the Statcom? This is the second part of the variable war generation, and this is the war generation by switching converter base. So it is a switching converter base. So switching converter base, second part. Converter type, war generation. Again, war generation means both generation as well as absorption. Generation means it is a capacitive reactive power, and absorption is the inductive reactive power. The switching base converter type war generation does not use the inductor and capacitor to generate and absorb the reactive power, whereas here GTO's gate turn off device as well as the IGBTs are used in the switching, means it is DC to DC to AC switching converter, and by this converter static war generation is going to obtain. But the basic operation, what is the basic operation? The basic operation can be understood with the help of synchronous mode. So it is a synchronous motor, and from this synchronous motor operation, we are going to develop the static switching converter type war generation. So this is the system voltage or transmission line V. It is connected with the coupling transformer. From coupling transformer, the inductor of the coupling transformer leakage reactance as well as the synchronous reactance. So this is the reactance X, and now this is the synchronous motor whose back EMF, say it is a E, that is a back EMF. We know that the back EMF of synchronous motor depend on the excitation. In case of DC motor, the back EMF is depend upon the voltage. Depend upon the speed, but the synchronous speed is constant irrespective of the load condition. And here the back EMF is depend upon the excitation. So this is the excitation, and back EMF, this is the voltage. So just we summarize the basic operation of the synchronous motor as a synchronous condenser. Synchronous motor as a synchronous condenser. Now, what are these different operations? We will take the back EMF, which is depend upon the excitation. So here, let the back EMF EB, or say simply back EMF E, is smaller than the supply voltage. What it means? It means that the excitation is small. So under excitation, power factor is a lagging power factor, and under lagging power factor, the VAR is going to absorb. It is going to absorb the reactive power. So it means that the reactive power going to flow in this direction. Whereas in the second case, when back EMF, it is due to the change in excitation. Back EMF is greater than the supply voltage. So it is over excitation, and the power factor is leading power factor, and here VAR is going to generate. In addition to these 2 points, means here the second case, the VAR is going to generate. It's going to deliver to the reactive power. Now, one more thing which we are going to say right over here. Under such condition, the active power, okay, say we'll take one more. Third case is the excitation EMF or back EMF is equal to the supply voltage, and it is work on the normal excitation. And under normal excitation, there is a unity power factor, and VAR generation or VAR absorption is 0. So this is 0. So this is the, you can write as a Q, is that one. Here we are writing as a Q, and this is also the Q is equal to 0. Now all three cases, the synchronous motor consumes, or here we are using the word absorb and generate. So absorb active power. So this is the one thing. In all cases, it is consuming the active power. This is the rotating part. So extra maintenance attention is needed. Whereas the reactive power generation is quite appreciable, because one may control the reactive power very easily only by controlling the excitation, and therefore it is called as a active compensation in the power system. But our objective is to produce static VAR generation. Our objective is to static VAR generation. And therefore, we are replacing this synchronous motor by a static device. So this system voltage V as it is, this is the line. Coupling transformer, it is the inductor of coupling transformer. It is not an inductor of simply just similar to the thyristor control reactor and thyristor switch reactor is there. So again, it is a coupling transformer. Now we are using a converter. So it is converter, switching converter. And one charge capacitor. Okay, so is it same? This is same. The diagram is same. Only this synchronous motor is replaced by the switching converter. So again, here the voltage of the converter is say VAC, and either it is going to deliver the current IAC or absorb the current IAC. So what would be the operation? Simply same way we can understand, say VAC, that is the converter voltage. If it is smaller than the V, definitely the current is going to deliver toward the converter and it will absorb reactive power. When VAC is greater than the system voltage, definitely it will deliver the current to the transmission line and it generate reactive power. So this is going to happen with the help of switching converter. It is a DC to AC converter, DC to AC switching converters. This is the current IDC and this is the DC converters are there. But in this case, the active power consumption or delivery is 0. Now, if same circuit is connected with the some part of energy storage system. So energy storage system, say this is the system voltage or transmission line. Same thing is there. This is the coupling transformer and all these things. I'm just to replace it by the equivalent circuit, means it is an inductor of the coupling transformer. This is system voltage and it is connected to the Statcom. This is nothing but the Statcom. Okay, so we will give the name as a Statcom. So here is a Statcom. So it is independent of the system voltage with the help of coupling transformer. And now energy storage device, battery, supercapacitor, superconductor, it is connected. So it is a energy storage. And the voltage, terminal voltage of energy storage is VDC. The current is delivered IDC. And this is IAC, definitely similar to the one. And this is VAC. Okay, this is the VAC. Now, under such condition, we try to understand with the help of some diagram. Say this is the, we are making some quadrant for understanding this one. And in this direction, this is the VDC. The current is IDC. Current is IDC. And in this direction, the current is minus IDC. Say this is the current also, IAC, and this is voltage, VAC. Very fast VAC. Now see, in this direction, in this diagram, we are assuming that when the DC current is delivered, it is a positive, therefore IDC and voltage also positive. But if the current is entering, means the battery charging system or some energy system getting the active power, so this current may be IDC. This is IDC. In this direction, it is a positive one. Similarly, the current which is in this direction, it is supplying is a positive, and in the opposite direction, definitely it will be a negative one. So in this side, it is the generation side, absorption side, generation side for the DC, and this is for the absorption side. Means here it is supplies active power P, and here consume or absorb the reactive power P. So in this quadrant, when VAC is greater than the system voltage and it is supplying the current, so under such condition, it supplies power P as well as supplies reactive power. So both are this one. But at the same time, when the voltage is smaller, the system voltage is smaller, definitely the reactive power is absorbed. So reactive power absorbs reactive power, whereas the voltage and current IDC is positive, so it is supplies active power. Here the IDC is positive. IDC is positive. Now, in this case, here the IDC is negative, means it is consuming the active power. So here we can say that absorb power P, and here also absorbs power P. But in this case, the voltage of Statcom is greater. So we can say that here the reactive power supplies reactive power, and whereas here the voltage of compensation or Statcom is smaller, so it is absorb reactive, isn't it? So this is the 4 operation quadrant in this way. So what is that? Just we will review. When the energy storage system delivering the IDC current, so it is a positive, and what it is consuming, so it is a negative one. Similarly, when the Statcom voltage is greater than the system voltage, it is going to supply the reactive power, that is generate. And when the voltage of Statcom is smaller than the system voltage, definitely it is going to absorb the reactive power. So in this case, the voltage VAC is greater, IDC is positive, so both are supplies. In this case, VAC is smaller, whereas IDC is positive. So the active power is going to supply, whereas the reactive power is going to absorb. In this case, the reactive DC current is negative. So in both cases, the active power is going to consume, so absorb the reactive power, and whereas supply the reactive power. So what is the advantage of Statcom over the TCS and thyristor control reactor and all these things? When it is connected with the energy storage system, so during transient condition, it supplies some reactive power or consume the reactive power to mitigate the oscillation in the system. So it will mitigate the oscillation system. It will mitigate as it is maybe connected in the midpoint, so it will increase or enhance the power handling capacity of the transmission line, existing transmission line. It will maintain the system voltage, that is end voltage supports also there, and the same things, it is also improve the transient stability. So this is the some summary lecture of shunt compensation. Thank you.